Deep in the cosmic archive of our galaxy's history, something profoundly unsettling is happening. Stars that have burned steadily for millions of years are simply vanishing from existence, disappearing from our telescopes as if they never existed at all. Imagine looking up at a familiar constellation tonight, only to discover that one of its brightest stars has completely disappeared by tomorrow, leaving behind no trace of explosion, no expanding shell of debris, no dying embers of cosmic fire. Just empty space where a massive sun once blazed with the fury of nuclear fusion. Recent astronomical surveys have documented hundreds of such inexplicable vanishing events. From the dramatic case of ASASSN-24FW, which dimmed by 97% over 8 months in 2024 before mysteriously reappearing, to the haunting disappearance of N6946-BH1, a red supergiant 25 times more massive than our Sun that simply winked out of existence in 2009 and has never returned. The Vanishing and Appearing Sources during a Century of Observations project, known as VASCO, has systematically compared photographic plates from the 1950s with modern digital sky surveys, documenting a cosmic census that challenges our most fundamental assumptions about stellar physics and the nature of reality itself. By meticulously analyzing nearly 1 billion celestial objects across 70 years of observations, citizen scientists and professional astronomers have identified 798 objects classified as truly vanished. Sources that shone brightly in mid-20th century surveys, yet have completely disappeared from modern observations, with detection thresholds reaching 21st magnitude, more than 100 times fainter than the original detections. Even more mysteriously, the project has discovered cases of multiple transients appearing and vanishing within confined regions of sky during single photographic exposures, including one extraordinary event from 1952, where 3 bright objects, each reaching 16th magnitude, appeared and disappeared within 50 minutes before remaining absent for over 70 years. The conventional explanation for stellar disappearance involves the catastrophic death of massive stars in supernova explosions. But these vanishing stars present a fundamentally different phenomenon that operates according to principles we have yet to fully understand. Failed supernovae represent one of the most compelling theoretical frameworks for explaining these mysterious disappearances, describing a process where stars more massive than 25 solar masses collapse directly into black holes without producing the brilliant explosions we expect from stellar death. Computer simulations suggest that when the core of such a massive star can no longer support itself against gravitational collapse, it falls inward so rapidly and completely that not even the tremendous nuclear energies released during the collapse can escape, creating what astronomers call a direct collapse event that transforms a blazing star into an invisible black hole in mere seconds. The case of N6946-BH1 provides the most compelling observational evidence for this exotic form of stellar death, representing what may be the first directly observed transformation of a red supergiant into a stellar mass black hole without an accompanying supernova explosion. Located in the galaxy NGC 6946, approximately 20 million light-years from Earth, this star began showing signs of unusual activity in 2009, when it produced a modest outburst that briefly increased its brightness before fading dramatically. Subsequent observations with the Large Binocular Telescope and space-based instruments, including Hubble and Spitzer, have failed to detect any trace of the star at optical, near-infrared, or mid-infrared wavelengths, suggesting that the progenitor has either collapsed entirely into a black hole or has enshrouded itself in such a thick cocoon of ejected dust that it remains completely hidden from our most sensitive instruments. Recent observations with the James Webb Space Telescope have begun to resolve this cosmic mystery by probing deeper into the infrared spectrum, where a dust-enshrouded star would be expected to emit thermal radiation from its heated envelope. If N6946-BH1 has indeed undergone a failed supernova and collapsed directly into a black hole, Webb's unprecedented sensitivity should detect no infrared emission from the location, providing definitive proof that a star can die by simply disappearing from the observable universe. However, if the star has experienced an extreme mass loss event similar to Eta Carina's Great Eruption, Webb should detect the warm glow of dust grains heated by the hidden stellar core, indicating that the disappearance results from obscuration rather than complete collapse. The discovery of binary star system VFTS 243, containing a massive star paired with a 10 solar mass black hole, provides additional evidence that stellar mass black holes can form through quiet collapse rather than explosive supernova events. The orbital characteristics of this system indicate that the black hole formed with minimal disruption to the binary configuration, requiring the absence of the asymmetric explosion and natal kick typically associated with supernova events. This observation supports theoretical models suggesting that up to 30% of the most massive stars may end their lives through direct collapse, explaining why astronomers rarely observe supernovae from the highest mass stellar progenitors, despite their predicted abundance in young stellar populations. Yet, failed supernovae represent only one pathway for stellar disappearance, and some vanishing events display characteristics that challenge even our most exotic astrophysical models. The phenomenon of multiple transients, where several bright objects appear and vanish simultaneously within small regions of sky, suggests processes operating on scales and timescales that transcend individual stellar evolution. The 1952 event documented 3 16th magnitude sources within 10 arcseconds of each other that vanished within 1 hour and have remained absent for over 70 years, implying they dimmed by more than 10 magnitudes in less time than typical stellar variability cycles. Such coordinated disappearances require explanation through either unknown astrophysical processes or exotic physics involving gravitational lensing of background transient sources by foreground massive objects with complex internal structure. The possibility that some stellar disappearances result from phase transitions in ultra-dense stellar cores opens another frontier in our understanding of extreme matter states. Neutron stars, the collapsed cores of massive stars that have undergone successful supernova explosions, contain matter compressed to densities exceeding that of atomic nuclei, creating conditions where the fundamental nature of matter itself becomes uncertain. Recent theoretical work suggests that at the highest densities found in the cores of the most massive neutron stars, ordinary hadronic matter composed of protons and neutrons may undergo a sudden phase transition to quark matter, where the constituent quarks of individual nucleons become deconfined and flow freely through the stellar interior. This hadron to quark phase transition could dramatically alter the structure and observational properties of neutron stars, potentially causing some objects to undergo sudden collapse or explosive reconfiguration that could render them temporarily or permanently invisible. Bayesian analysis of neutron star observations suggests that the equation of state of ultradense matter exhibits a peak in the speed of sound that exceeds the fundamental limit imposed by special relativity, indicating the presence of exotic matter phases that behave according to principles beyond our current theoretical understanding. The existence of hybrid stars containing both hadronic outer layers and quark matter cores remains observationally unconfirmed, but the discovery of neutron stars with masses approaching 2.4 solar masses suggests that some compact objects may indeed harbor exotic matter phases that could undergo sudden transitions. Even more exotic explanations for stellar disappearances involve the fundamental structure of space-time itself and the possibility that our universe exists in a metastable false vacuum state that could undergo catastrophic transitions to lower energy configurations. In quantum field theory, vacuum decay represents a process where regions of space spontaneously transition from higher energy false vacuum states to lower energy true vacuum states through the nucleation of expanding bubbles that propagate at the speed of light. Recent experimental work using ultra-cold atomic gases has demonstrated the nucleation and evolution of such vacuum bubbles in laboratory settings, revealing the complex dynamics of phase transitions in quantum field systems. If our universe exists in a false vacuum state, as suggested by some interpretations of particle physics data, then high-energy astrophysical events could potentially trigger localized vacuum decay events that would fundamentally alter the properties of matter and spacetime within expanding spherical regions. Stars caught within such vacuum bubbles might experience rapid changes in the fundamental constants of physics, including the masses of particles and the strengths of fundamental forces, potentially causing them to dissolve or undergo transformation into entirely different types of objects. While the likelihood of such vacuum decay events remains extremely small, according to current theoretical estimates, the existence of unexplained stellar disappearances raises the possibility that we may be observing the signatures of physics operating beyond the standard model of particle physics. The potential role of primordial black holes in triggering stellar disappearances represents another frontier in exotic astrophysics, connecting the vanishing star phenomenon to the earliest moments of cosmic history. Primordial black holes, formed from density fluctuations in the early universe rather than stellar collapse, could have masses ranging from microscopic scales to thousands of solar masses. The smallest primordial black holes would undergo rapid evaporation through Hawking radiation, releasing tremendous amounts of energy in their final moments as they shrink to subatomic scales. The evaporation of a primordial black hole in the vicinity of a star could inject enormous amounts of high-energy particles and radiation into the stellar environment, potentially disrupting stellar structure or triggering catastrophic instabilities that cause the star to collapse or explode. Recent calculations suggest that the breakdown of Hawking evaporation physics for the smallest black holes could significantly extend their lifetimes, allowing primordial black holes with masses below 10 billion kilograms to survive until the present epoch. The explosive evaporation of such objects near stars could create transient events that temporarily outshine the host star before causing its disappearance through unknown mechanisms. Advanced theoretical models propose that stellar disappearances might result from interactions with objects or phenomena existing in dimensions beyond our familiar three-dimensional space. String theory and M theory suggest that our observable universe represents only a small subset of a larger 11-dimensional reality, where additional spatial dimensions remain hidden from direct observation, but can influence physical processes through gravitational and exotic field effects. If massive stars occasionally interact with higher dimensional objects or fall through dimensional boundaries, they could disappear from our three-dimensional reality while continuing to exist in regions of space-time inaccessible to our instruments and observations. The discovery that some vanishing events show evidence of coordinated disappearances across multiple objects suggests the operation of processes that transcend individual stellar physics. The linear arrangement of some multiple transients hints at the possibility of interactions with extended objects moving through our cosmic neighborhood, such as cosmic strings or other topological defects in spacetime that could cause temporary or permanent alterations in stellar visibility. Such exotic structures, predicted by various cosmological models but never directly observed, could create localized distortions in spacetime that render stars temporarily invisible or cause them to undergo rapid evolutionary changes that remove them from observational detectability. The temporal characteristics of stellar disappearances reveal additional clues about their underlying physical mechanisms, with timescales ranging from hours to decades, suggesting the operation of multiple distinct phenomena. The rapid dimming of Assassin 24FW by 97% over 8 months, followed by its complete recovery to normal brightness, indicates reversible processes that can dramatically alter stellar visibility without permanently destroying the star. This behavior contrasts sharply with the permanent disappearance of objects like N6946-BH1, suggesting that stellar vanishing events encompass a spectrum of phenomena, ranging from temporary obscuration to complete transformation or destruction. Statistical analysis of the VASCO catalog reveals that vanishing events occur at rates significantly higher than predicted by conventional models of stellar evolution and death, implying the existence of physical processes not accounted for in standard astrophysical theory. The distribution of these events across different stellar types and galactic environments provides constraints on possible explanations, with some models favoring exotic physics scenarios over conventional astrophysical processes. The absence of associated electromagnetic signatures in most vanishing events, such as the optical transients expected from supernova explosions or the X-ray emission anticipated from black hole formation, suggest that these disappearances involve mechanisms that operate through channels largely invisible to our current observational capabilities. Future observations with next-generation telescopes, including the James Webb Space Telescope, the Extremely Large Telescope, and gravitational wave detectors, promise to provide unprecedented insights into the nature of stellar disappearances. Multi-messenger astronomy, combining electromagnetic observations with gravitational wave and neutrino detection, could reveal the hidden signatures of exotic disappearance mechanisms that produce minimal electromagnetic output but significant emission in other channels. The systematic monitoring of stellar populations across multiple wavelengths and timescales will enable astronomers to distinguish between conventional astrophysical explanations and more exotic scenarios involving new physics or higher dimensional phenomena. The profound implications of stellar disappearances extend far beyond astrophysics, touching on fundamental questions about the nature of reality, the stability of physical law, and our place in a universe that may harbor phenomena operating according to principles we have yet to discover. If some vanishing events result from vacuum decay or higher dimensional interactions, they represent our first observational glimpses of physics beyond the standard model, operating on cosmic scales. The possibility that stars can simply cease to exist challenges our most basic assumptions about the conservation of energy and matter, suggesting that the universe may be far stranger and more dynamic than our current theories predict. As we stand at the threshold of a new era in astronomical observation, equipped with instruments capable of monitoring billions of stars across cosmic time, the mystery of vanishing stars represents one of the most profound challenges to our understanding of stellar physics and the fundamental nature of reality itself. Whether these disappearances result from exotic stellar death mechanisms, interactions with higher dimensional physics, or entirely unknown phenomena, they remind us that the universe continues to harbor secrets that transcend our deepest theoretical understanding, inviting us to expand our conception of what is possible in the vast cosmic theater that surrounds us, and to prepare for discoveries that may fundamentally alter our understanding of existence itself.